Okay, let's look at example 1215. We got a race car going around a horizontal circular track, meaning this thing is level. We will look at banked turns where a car might be going around a turn this way, and it's banked at some angle like a racetrack at some other time. But right now this is a horizontal track, so that's a key word in this problem. It has a radius of 300 feet, so it's circular. If the car increases its speed at a constant rate of 7 feet per second, so that would be its tangential acceleration. Determine the time needed for it to reach a vector acceleration of 8 feet per second. It doesn't say vector in the book, but you need to know it's actually talking about a whole magnitude is 8 feet per second, not the component they gave us. So why would it have a bigger magnitude at some time if it has a constant acceleration as it speeds up? Because of our v squared over rho normal component. As that component gets bigger and bigger, it'll eventually add. We will have a component in the tangential direction. We know what that is already. That's equal to a constant 7. We will also have some normal component. And when we add those together, that 7 plus whatever this is will give us a magnitude of 8. And they want to know how long it takes to get there and then how fast it's going at that point. So it's a fun little problem. First, we should realize that the acceleration magnitude can be found by this equation. We square both components, add them together, and take the square root. We know that the tangential component is 7 feet per second. All we know about the normal component, though, is that it is v squared over rho. We know the rho, though, so we can go ahead and say b squared over 300 if we want to. Alright. Now, we want this to add up to be 8. So far we have 8 is equal to, going to make that big, 7 squared plus, now what do we put in the rest? Well, if we know it started from rest, I'm going to make a little side box, started from rest and it accelerated, then we can, with a constant acceleration, we can use constant acceleration equations to look at its linear speed, basically. What's its speed as it goes around? And what does its speed have to be to have a v squared over rho component a big enough one to make our magnitude end up being 8. So constant acceleration equation, v final is equal to v naught plus the acceleration in the tangential direction times time. We started from rest. Therefore, we get a final velocity as the acceleration times time. Okay, well, let's go ahead and plug that right into the normal component as v squared over rho. I'm going to say it's now the tangential component times time over rho, or the tangential component times time over 300. Okay, so I'm going to plug that in here now. The acceleration times in the tangential direction times time divided by 300, and that's all squared. We also have this acceleration in the tangential direction, so we can go ahead and put a 7 in there. Right, this is equal to 7t. Now we have an equation with only one unknown, the time. Solving this would require us to take the positive root. We would have we get 0.163 t squared is equal to the square root of 8 squared minus 7 squared. T ends up being, taking the positive root, 4.87 seconds. Alright, that's what they wanted to know. How long does it have to accelerate at 7 feet per second until we get an acceleration vector, this thing right here, to grow from its initial 7 to 8, because we're adding a normal component. Alright, one more thing, it asked what the velocity was then. Well, we can go back to the fact that the velocity was equal to 7t, and plug in t. We know the time now. 7 times 4.87, get 34.1 feet per second, and that's the speed. We didn't have any direction given to us, so I have no idea what the velocity is. Alright, thank you. Oh.